Welcome to part two of a walkthrough of copy suppression, comprehensively understanding an attention head. In this part, we're going to be doing a deeper dive into exactly why we claim that we've comprehensively understood this head, what we mean by that, and what evidence we've collected that the only thing it is doing is copy suppression. Callum, do you want to walk us through at a high level the different lines of evidence we have?
Essentially, at a high level, I would split the evidence that we have into three different parts. Firstly, there's the part where we analyze the QK circuit in depth. Firstly, there's the part where we analyze the OV circuit in depth. So this is like how the model's mapping from input to output actually works. Like when it attends to something, what information is it moving from source to destination token? We do both static analysis and dynamic analysis on this. So by static analysis, I mean just looking at weight matrices and not considering it on any actual real inputs. And in dynamic analysis, I mean actually considering it on real inputs, seeing what the outputs are. We'll get into the details of this when we actually discuss this. First section, OV matrices. Second section, QK matrices or attention patterns. We figure out how it is deciding what things to attend to. Again, we do static and dynamic analysis. We will both look at the weight matrices, and we will also look at actual examples of attention patterns in real inputs. And then finally, the third section is the big one, where we bring everything together and we define a particular form of ablation, which we essentially claim removes everything about the head except for the exact copy suppression mechanism, which we think is going on and which we think explains this head. And we judge the amount that we've explained about this head by how well our ablation works.
So to recap that back, there's two ways you can analyze a bit of a model. One of them is just by doing weights-based stuff. Rather than giving the model any inputs, you just actually analyze the model's parameters and what they mean and how it all fits together. In particular, as I explained in my walkthrough of a mathematical framework for transformer circuits, an attention head is determined by two separate matrices, the QK matrix and the OV matrix. The QK matrix determines where the attention head looks, from what destination tokens to which source tokens. The OV circuit determines, once it knows what source token it's looking at, what information it extracts from that source token and moves to the output. And we show that the QK circuit is all about look at things that are going to be predicted, and the OV circuit is all about suppress whatever you look at. We then also do a dynamic analysis, where we run the model on a bunch of text and see what happens, and show that most of this is copy suppression. With dynamic analysis, one of the key questions is what distribution are you sampling your text from? And here we use open web text, which is an open source replication of the GPT-2 training data. So as wide a set of data as we can get that GPT-2 is designed to have opinions on. We show that most of what's going on is genuinely copy suppression via this slightly backwards way of thinking of stop the head doing anything that is not copy suppression and verify that it's still as good. Do you want to walk us through the QK and OV results?
We can start with the OV circuit, zoom into an appropriate amount. The key thing for the OV circuit is that we think the primary function of the OV circuit is to take in the embedding of a particular token and output the negative of that token's unembedding. There are a bunch of things that get stored in the residual stream at any given position in the model, but we think that the only thing that really matters for that is the embedding. One way we can measure the effect of the OV matrix on the model's embeddings is by constructing this full matrix, which has size devocap by devocap. So in the case of GPT, this is 50,000 by 50,000. Essentially, on the input side, basically put this matrix, which is something we call the effective embedding matrix. We can return to this in a couple of minutes, but essentially what this is a proxy for the embedding matrix, which takes into account a particular subtlety of how the model works and how we should interpret embeddings in this model. But for now, we can just pretend that this is actually the embedding matrix. This is basically the matrix containing all of the embeddings of every single token in this model's vocabulary.
Where an embedding is just the representation of that token as a vector in the model's residual stream at the first layer.
Yeah, exactly. It's just, this thing's just a learned parameter of the model. Then on the output side, we put the unembedding. So again, it's just a matrix of hidden size by 50,000, which consists of all of the unembedding vectors for the words in the model's vocabulary. This is the matrix that you apply in order to get the linear map from the final state of the residual stream to the output logits. So this entire thing has size about 50,000 by 50,000, and the interpretation of each row of this matrix, the interpretation of each column of this matrix is essentially the ith column, for instance, is how the logics get affected if you are attending to a source token, which is the ith source token in the model's vocabulary, pretending that the only thing that is present at the source token is this particular word, how are the logics affected? And the thing that we expect to find is that the most affected logit is the logic for that same source token, or as the ith logit, and we expect this is pushed down significantly. In other words, to recap, in this 50,000 by 50,000 matrix, we expect to find that in the ith column, the most negative element is the ith element, and we expect this to be true for all values of I. Before we present the results for this, I guess it's worth discussing this thing here, which is like not actually the embedding matrix, this is the effective embedding matrix, is what we've been calling it. This is essentially because of a subtlety in GPT, GPT-2, that is also like somewhat common in a few other different types of models. GPT-2 has what's called a tied embedding matrix, which means that essentially this matrix here and this matrix here are essentially the same. They share the same weights and they are updated in the same way when the model gets trained. This is a little bit difficult because it essentially means that the model has restricted freedom of like this embedding matrix and this unembedding matrix. It can't represent things like bigram frequencies, for instance. And so in practice, what the model ends up doing is repurposing the first MLP layer as some kind of extended embedding matrix. So like rather than it being best to think about the like actual embeddings that are at the very start of the model as the actual token embeddings, you can look at what the values are in the residual stream at the end of the first layer, like after you actually apply the first MLP layer. And this is much more representative of like a thing that you would think of as an embedding, because it like has the freedom to be different than the unembedding vector. In practice, we can create some kind of proxy for this effective embedding by just like applying the MLP naught, which is like a deterministic function, to each vector in the embedding matrix. And this gives us like a new matrix, which we think is like a better representation of like what the model's embeddings actually are. Yeah, there's a fair amount of literature like justifying different choices of like embedding matrix. I believe we did some like sanity checks on this by essentially measuring whether you could substitute the value in the residual stream at the start with like this matrix, pretending that actually no information gets moved between different sequence positions in the very first layer, and like seeing how much is affected loss. And it turns out that it doesn't really. So this is a like good approximation for what is in the residual stream by the end of the first layer.
Just to kind of recap the key points in there, it is empirically the case that often in circuits, when you expect part of the circuit to be using the token embedding, like the name movers look at the name Mary or something, they actually mostly look at the output of MLP0. Our hypothesis for why this is going on is that MLP0 is predominantly just responding to the token embeddings, even though there is also attention 0 in between them, and it could be moving information from other tokens. Empirically, this doesn't seem to be an important part of what goes on in the model. And it seems that MLP0's output is predominantly a function of the token embedding and kind of treated as a token embedding, like which we call the effective embedding. You could think of it as MLP0 of the embedding plus the embedding, or MLP0 of the embedding plus the average of attention 0, or anything else. For simplicity, we've just gone with MLP0 of the embedding because it doesn't really matter. The MLP0 has like a much larger norm than these other terms, so it kind of drowns them out. I don't actually know if this happens in models that don't have tied embeddings and unembeddings. Our hypothesis is the reason this happens is that the model wants to break the symmetry between the embeddings and the unembeddings. But the only untied models I've studied have parallel attention, which means that MLP0 never sees attention 0, so it is literally a function of the embeddings. So it kind of has to be factored into the embeddings.
Yeah, in upcoming work on successor heads, we find similar importance of MLP0 in the Pythia models. So evidence does point towards, for some reasons, models using this MLP0 as the embedding.
Yeah, I mean, Pythia has parallel attention. So it's like, it would be wild if it didn't use MLP0, because MLP0 can be doing nothing other than being a lookup table. Yeah, I'm partially just highlighting this because I think this is the kind of genuinely quite important methodological detail that can make or break an analysis, but you often kind of skim over when reading a paper or get cut for space, as we found with conference page limits.
Yeah, and I guess for the listener, maybe it's easier to start with the mathematical framework explanation of the OV circuits, because we literally have an OV circuit here in their notation, but we're just wrapping the embedding matrix in this MLP0. But yeah, as Neil mentions, this is crucial to actually get interpretable results. So it's not just a trivial application of what was done before.
And yeah, OV, just to unpack, is you take the value matrix and you multiply by the output matrix. And we just think of this whole thing as a low-rank factorized d-model by d-model matrix. All right, sorry, I keep cutting you off, Callum.
No, that's fine. I was just going to say reference back to mathematical framework and also to clarify the point about breaking symmetry. Yeah, mathematical framework shows you can decompose the output of a transformer into the sum of a bunch of different paths. Easiest one for a transformer to essentially learn is the direct path, which just goes through the embedding matrix and the unembedding matrix and the output. If the embedding matrix and the unembedding matrix are tied, then that means that this path is symmetric. So if your input token is Barack and you predict Obama, then it follows that if your input token is Obama, you should also predict Barack to follow it immediately. And this is kind of bad. We obviously see why this is the kind of thing we don't want to happen. And this is one sort of motivating example of why we might want some extra thing to break the symmetry, to make it so the embeddings aren't just the same as the unembedding.
So, all right, we've ended up with a 50,000 by 50,000 matrix. So we need to do something to try to understand it. How do we go about that?
To recap the thing we're hoping to do, we're hoping to find that for every column, the most negative element is the element on the diagonal. Because this does strongly suggest that at least part of what this head is doing, part of what this OV circuit is doing, is suppressing the token which it pays attention to.
And yeah, just to remind people what that matrix means, is 50,000 by 50,000. For every token in the vocabulary, say John, which is token 20,000 or something, this says if head 10.7 looks at John, how does that directly affect the output logits? This directly affects the output logits for all 50,000 possible output tokens, and we would like the biggest negative number, or the smallest number, to John. John mapping to John is on the diagonal. So we kind of want the diagonal to have a really low rank, or a really high rank. It should be the smallest thing.
Yeah, so this is what we're hoping for, and yeah, it's exactly what we find. In about 85% of situations, the diagonal element is one of the 10 most negative elements in the entire column. And if instead of that you relax to just in how many cases is the diagonal element in the bottom 5%, most negative examples, this goes up to 98.86%. So yeah, pretty close to everything. Yeah, there's actually a pretty interesting observation that we found, which is that in the cases where the most negative element is not the diagonal element, it ends up being the token ID of a token which is semantically similar to that token. So, for instance, if the token was I don't know, bird, then maybe the most negative token is actually birds, something that's very close to that token, but is related by, a pluralization or a tense or something. And maybe we'll get a little bit more into the implications of this semantic similarity result later on. But it does it's another interesting observation that we found while we were doing this work. Also, when we're talking about the OV matrix and the effect that it has on output, one important question which we kind of glossed over so far is this head more important because of how it affects the final output, or is it more important because of how this head affects other attention heads? Is the output of this head being used by heads in layer 11, essentially? And this is what we investigated by essentially, we'll probably skim over the technical detail because this isn't the most interesting thing to dive deeply into. But in essence, what we did was a few different experiments where we separated out the different paths that sort of went from the output of head 10.7 to the final logits. We separated out the direct path from 10.7 to actually directly affecting the final logits just by what this head adds into the residual stream. And we also look at the paths that run through other attention heads in layer 11 before getting to the final value in the residual stream. And we find that no matter essentially what way you measure it, what metric you use, the most important path is the direct one from 10.7 to the final logits. And this is why we feel justified in essentially saying, to understand head 10.7, we just need to understand its output and how it affects the logits. We don't necessarily need to think about how its output is used by other attention heads.
All right, so we basically understand the OV circuit. The head looks at a thing and it suppresses the thing. It's almost always the top 10 out of 50,000. And I think you had some really cute results about what the remaining 1.14% were. Do you want to talk about those? Yeah, the tokens which aren't suppressed.
Yeah, this is going to be cute and interesting results. When we looked at all of the tokens which didn't have like super negative ranks along the like full OV matrix, we found that when you filter out the tokens which are like in the first 256 tokens, like ASCII 256, the ones that you're left with are a very small number of very anomalous tokens, like that show up super rarely in GPT's vocabulary, so in like OWT in the text that's trained on. And the vast majority of the remaining tokens were what we would call function words. So, words like his and of and at and then, and variants of those words with like spaces and capitalizations and stuff. This is kind of interesting because it definitely shows that the model is doing some kind of nuanced smart thing. It doesn't necessarily tell us exactly what that smart thing is, but it at least shows us that the model is doing something more advanced than just suppress whatever word it is attending to. It is like carved out an exception for whatever reason for these function words. We did discuss this result in the context of some of our theories of how this head forms, and it was actually a result we had predicted based on one of our theories. So as we discussed in the previous video, one of our theories was that this head forms to suppress naive copying, because most words in GPT's vocabulary have the property that if they appear in a prompt, they will probably appear later in that prompt. And so maybe heads will like learn to copy those words, and then heads like 10.7 evolve to suppress that copying. But function words don't really have this property. They don't have what we call the positive update property. Because just the fact that you see them in a sentence shouldn't really update you on them being like more likely to appear in that same sentence or like in another sentence. I mean, like it updates you that, I don't know, the language is English or something, but hopefully the rest of the text does that as well. They don't update you in the same way that you see the word John, and you're probably talking about someone called John, and so John is likely to appear later in the sentence. Or like, even a noun or a word that carries like more information about the text. Function words aren't like this. If you see a function word, you shouldn't positively update on it appearing like later in the prompt any more than you would think it did by default. So it stands to reason that maybe copying behavior, like naive copying, doesn't form for function words. And so 10.7 never actually needs to copy suppress them. This is like quite a long chain of reasoning, and it's very possible that it's like completely wrong. But it did allow us to predict this in advance. So maybe we at least win like some base points.
And yeah, I think the meta-level technique here is worth highlighting. If you have some technique or some way of selecting for things, analyze the errors, the cases where the technique fails, and see if there's a pattern. Often the exceptions you get will kind of support the broad story you are trying to tell in a way that makes your results stronger rather than weaker.
Definitely, yeah. And actually, this is also a theme that came in when we were working on our ablation, or to explain it in terms that are more like understandable at this point in the talk, when we were developing our like exact mechanistic story for what copy suppression was. Because we often found ourselves getting into a flow of, here's a mechanistic story for copy suppression, let's apply it to our model and like see what examples slip through the cracks. Let's see if any of those examples actually look like they are copy suppression. And if they do, see why our model missed them. And like refine our model so that we're picking them up, and keep doing that until we're confident that all the examples our model are missing are not actually copy suppression. And yeah, this like ended up being a way that we discovered like a bunch more things, like the semantic similarity results, which we discussed a little bit, and maybe we'll discuss like a bit more later on.
Yeah, let's just dig into the semantic similarity now. What's semantic similarity?
Nice, yeah. Broadly speaking, semantic similarity, as we mentioned, is when two tokens are like basically have the same meaning, but they differ in small ways. The most common like 4 ways for this to happen are prepended space, capitalization, or like some other grammatical quirk like tenses.
An important fact about tokenizers and language models is that they get given text, which gets converted to these tokens and some fixed vocabulary by a tokenizer. And there are different entries for tokens that begin with a space or not. There are different tokens for capitalized and non-capitalized tokens. And like often these will be really similar.
And also speaking of tokenization, there is a fifth example which we're still classifying as semantic similarity in this context, which is if there are 2 variants of a token, say one has a space prepended and one of them doesn't have a space prepended. If one of those versions gets tokenized, like split up into 2 separate tokens, but those tokens are so distinctive that they must only have come from tokenizing this word, then we also define them as like being semantically similar. To give an example of like this particular thing, and one which we actually saw in open web text, we can probably navigate to the example now, but the word Berkeley with a space is tokenized as the full word Berkeley. The word Berkeley without a space is tokenized as Ber and then Kelly, that's split into two different tokens. And it turns out that if you look at like the OV matrix and you take the column that corresponds to Berkeley with a space, then the most negative element is actually the Kelly token, the thing that you get when you take the Berkeley word and like split it in half. So what this tells you is that if you are attending to the Kelly token, the thing that you will suppress is the full word Berkeley. And this turns out to be pretty useful because there is one example in open web text where the word Berkeley with no space appears like earlier in the prompt, and it's split into Ber and Kelly. And later on in the prompt, the model is predicting Berkeley with a space, and so it attends back to the Kelly token, and the thing that gets suppressed is not the Kelly token, it is the Berkeley token with a space. Yeah, to recap the like high-level idea here, this is a way in which the model can do copy suppression in spirit without literally doing copy suppression. In other words, without the like token being predicted literally being the same as the token it's attending to. They're like extremely similar, and they are similar enough for this thing to like still be called copy suppression because the words are like basically the same up to some weird quirk. But you still get the main effect of this behavior is not to suppress the source token, it's to suppress the token that was being predicted.
All right, QK circuits.
So QK circuits, the static analysis was pretty much the same, had the same principle as the OV circuit, basically. So again, we define like another devocab by devocab size matrix, or nvocab by nvocab.
Conceptually, what this matrix means is that if your query is purely built from the unembedding of a certain token, and your key purely comes from looking at a certain source token, what is the dot product of that query and key? This is a devocab by devocab matrix for all possible pairs of tokens, and we can just compute it from the weights, and it's glorious.
Yes, and again, note that we've put the effective embedding on the key side because this is like a more representative archetypal thing that will be in the residual stream representing this particular token.
Where, importantly, last time, the WU represented the output of the head directly connects with the output of the model. How does that affect the logits? Here, the WU is entering the query of the head, and this is simulating a naive copier that, say, outputs love. And we're just like saying, oh, something output love. Let's look at what's up with that.
This matrix is telling us if you are predicting a token at the destination position of the query and a token exists at the key position, what are the attention scores between those two things? This is like a key distinction that's important to understand. In the OV section, we were dealing with a map from like devocab space to devocab space. Here, we're dealing with a bilinear form that like gives us our attention scores.
Yeah, and that's also like a departure from the original Anthropic mathematical framework introduction of the QK circuit, because their version, I believe, had a QK matrix in the middle of their expression, but then an embedding matrix on both sides to basically measure like, well, if the embedding at this current position was like this token, what will we attend to in context? The same token, a different token, and something like that. Whereas here, we're like designing this around the copy suppression hypothesis. That in fact, what the query like matrix will pick up on is unembedding vectors, which is kind of surprising, like a priori, but clearly the evidence thus far has been like behavioral that this goes on, and now like in this section we'll get like a weight space story for like what the hell this like head is really doing.
Yeah, like the key thing is that we're on the query side, these vectors, the unembedding vectors, we shouldn't expect them to be in the residual stream like at the start. They are things that are written to the residual stream like by these earlier heads.
Yes. Though we'll later discuss that we do need to distinguish from the hypothesis that they're just there because this model has tied embeddings. And so maybe they're just there from the tokens. All right. So again, we have a matrix, this time representing if the earlier component decided to output token X, should I look more or less at token Y? And what do we get when we do the same summary statistics on this matrix?
I think actually just from these statistics, they're even a little bit stronger than the OV results. We get that about 95% of the diagonal values are not just like in the top 10 or in the top 5. They are the largest in their respective rows. Note that we're saying largest rather than smallest, because in the OV circuit, we were looking at which tokens get suppressed the most. But in the QK circuit, we're looking at which attention scores are the highest. Like, for a given token which is being predicted, which source token will it attend most to out of all possible words in the vocabulary? And yes, it turns out that it is that same thing that is being predicted that it will attend to. One difficult thing which we did allude to in an earlier section was we don't quite understand the queries as much as we'd like to. These weight-based analyses, they're great, and they definitely tell us that something is happening, but they don't tell us that this is the only thing that's happening. We know that there is a certain extent to which the unembedding of a particular token will attend back to the embedding of an earlier token, but there could be other things at play. There could be other parts of the residual stream on the query side that are also important that aren't captured by this particular view of the matrix. And yeah, it turns out that, and yeah, we will omit the in-depth technical details. Unfortunately, this kind of is the case, and there are bits of the query that we don't fully understand. To take the IOI circuit as an example, yes, it is true that the name overheads 9.6 and 9.9 do output the unembedding of the IO token, and this unembedding is important in getting the head 10.7 to attend from this token back to the original IO token. Although that is true, it is also the case that heads 9.9 and 9.6 output something which is not the unembedding, but which still causes this head 10.7 to attend back to the IO token. Yeah, we did a lot of in-depth analysis on IOI. There are a bunch of different hypotheses we discussed, maybe it's got something to do with positional embeddings. But yeah, in the end, we did conclude that there is this component independent from the unembedding of the predicted token, which does influence the attention patterns. Yeah, we would love to understand this better. I think we'll probably chat more about this in the third section of this talk.
We have fully understood the head. All of its weights are laid bare before us. It makes perfect sense. It is fully explained and we can go home, right? The correct answer is not quite. And the main thing this is missing, as Callum was saying, is that we're kind of making this assumption here that nothing else in the model matters. We found one pathway from MLP0 on the source token and the unembedding straight to the unembedding, or MLP0 on the source token and this previous predicted unembedding vector on the query side. But maybe there's lots of other stuff that matters. In fact, there is at least some other stuff that matters. So it's also valuable to look at this on the whole distribution and see if our thing broadly holds up.
This is also where we move from static analysis to dynamic analysis, because we don't just want to show these weight matrices have some particular property when we consider them isolated from any possible input. We actually want to test our theories about this is the only part of the matrices that matter or whatever, by doing a particular causal intervention on our model and seeing how much the output changes. At a high level, this is the kind of thing that we wanted to construct going into this section. We wanted to construct some kind of intervention where we could wipe away everything except for the distilled essence of the copy suppression algorithm and still show that this head had good performance. Because if we can do that, then absolutely great. We've fully captured this head's behavior. One alternate approach that we could have taken, by the way, is isolate the specific copy suppression mechanism, delete that, and then see how much of the head's performance is harmed. There would also be a case for this. The main reason that we sort of went for the other response, the other approach, is that it's basically a higher bar to demonstrate a particular serve up a particular algorithm and show that this algorithm is actually sufficient for capturing the model's performance, not just necessary but also sufficient. And if we just have that algorithm, then the head behaves just like it does normally. It has the same effect on loss, it has the same effect on the distribution of outputs, all that.
Yep. Where the countervailing hypothesis is maybe there's three things that all matter. If you delete two of them, you expect it to go badly, and if you delete one of them, it will look like this was the only thing that mattered, when really it was one of three things that mattered. Yeah, generally, I quite like the structure we have in this paper of static and dynamic analysis. I think static is the weights-based is a lot purer and feels a lot more rigorous to me. Yep, we just fully understand this thing. We can literally read the algorithm off the model weights, but it also relies on a bunch of assumptions and simplifications. And dynamic analysis helps reinforce the idea that, yep, this is legitimate analysis that holds up. We were right to ignore these things. But yeah, do you want to walk us through CSPA?
Sure. Oh, sorry, just close the door. Yeah, and I also mentioned that on a meta level, the whole static to dynamic analysis thing is a pretty good research flow, because static is typically pretty cheap to formulate experiments for, pretty fast to test. And once you have those results, if they're falsified, then go back to the drawing board. But if they're good, then you can progress to something dynamic, which hopefully tests your hypothesis a little bit more. And yeah, that brings us to the diagram, which illustrates the ablation that we're calling CSPA, or copy suppression preserving ablation, which is a bit of a mouthful. The idea being that it preserves copy suppression and it deletes everything else. We think about this algorithm in a modular sense. We have like an ablation on the like OV circuit side, on the input-output side, and we also have an ablation on the QK side, on how it calculates the attention patterns. The full CSPA algorithm is combining both of these two ablations. The ablations are like illustrated here. We'll start with the OV ablation. We're taking the like all fair in love and war example, where the model naively predicts that love follows and yeah, we'll see how this ablation works. What we're illustrating here is that with and being the destination token, for every possible source token, every possible token that appears before and in context, you can apply the OV matrix to calculate the vector that is going to get moved from that position to the destination token if the destination token attends there. But what we can do is, instead of actually moving that token, we can move that token projected onto the unembedding. Instead of moving the vector, which is like the vector in this residual stream mapped through the OV matrix, we can take the vector mapped through the OV matrix and then project it onto the unembedding vector for this particular token. Because remember, our hypothesis is like the only information that, for instance, gets moved from love to the and token is the negative of the unembedding vector for love. So if we project this thing onto love, and we project this thing onto the unembedding vector for in, and so on, and we do this for all source tokens, then we're basically making sure that the only information that can move from source to destination is the effect that that vector has on the prediction of the source token. And yeah, more specifically, what this negative sign is illustrating is we're not just projecting, we're also projecting and taking the negative component. So actually going one step further. We're saying like the only vectors we are allowing to move from source token to destination token is the effect that this like vector will have on suppressing the prediction of that thing's source token.
So what we're doing is we're saying it looks at love and it tries to output a whole bundle of stuff, but we're only going to let it output the component of that bundle of stuff in the unembedding direction of love, the direction that will directly affect the love logit. We're not projecting it onto the space of all unembeddings. It is the unembedding of that token that was attended to. So love has a different projection from in. And finally, if for some reason the head was going to boost the logit rather than suppress it, we'll set that to 0.
Yeah, retelling this, let's say that the and token is attending to love. If it is doing that in order to boost love, we would be deleting that. If it is attending to love in order to boost any token other than love, we would be deleting that. The only direction that we are not deleting is the direction that corresponds to I'm attending to love so that I can suppress the prediction of the love token.
And the negative part is like actually fairly important because there are a bunch of heads that are doing copying. These heads show up reasonably well under the copy suppression preserving ablation if you allow the positive parts of the OV ablation as well, right?
Yes. Yeah, that is correct.
All right, QK ablation, which notably is qualitatively different from the OV ablation. It's a mask, not a projection. What's up with QK ablation?
Yeah, so basically with QK ablation, let's recap the idea. The reason that we think like the and token attends back to the love token is because love is already being predicted here. You have plus love in the residual stream, which is like something that we think is naively copied there by, say, an earlier attention head. So what we can do in this case, look at the tokens which are being predicted in the residual stream, and note that when I say being predicted in the residual stream, in this context, I mean using the logit lens. So basically, if you apply the logit lens to the residual stream before head 10.7, this kind of gives you, as Arthur was discussing, a sense of what the model is predicting at this particular time. If you apply the unembedding matrix, which tokens are the ones that the model assigns highest probability to. Given that the model is predicting love at this particular instance, we think that that is why it is attending from this and token back to this love token. And so what we can do is basically look at all of the tokens in context, pick the, say, 5% of source tokens which are most strongly predicted when you apply the logit lens at the destination token position, and only keep the vector that is moved from those source tokens. So you're ablating the attention to any other token which is not already being predicted at this particular position. And yeah, key thing here, this is not the same thing as the OV ablation. The OV ablation was a projection of the output. What we're doing here is a filtering. where we like say for 95% of source tokens, we're just not going to move any information from that source token to the destination token. We're only going to move information from the 5% of source tokens which are already being highly predicted at the destination token.
And importantly, this is a weaker ablation than we'd hoped for, but we could project the query onto the unembed direction.
Yes, if we could project the query, it would be great. Sadly, this was like something that was not super successful. It wasn't terrible, but like it definitely didn't get us like the kind of results we were hoping for.
Yeah, what are the numbers we get?
Yeah, there's like a few hacks you have to add on to like the projection to get this set up. We got up to like 61% recovered with some like hacks that upweight certain tokens, but by default it's like 25% of performance if you literally just project onto the vector. So you like the semantic similarity buys you a few percentage points, and there are like further hacks. But I got up to 61% and couldn't do better with projection methods.
Well, the projection methods were things like, with the tweaks were like, it copy suppresses proper nouns a bit more than normal tokens and stuff like that.
Yeah, like the first improvement made was the semantic similarity thing introduced, where you didn't just look at like how much is it predicting the word love, but also love with a capital L and love without a space and stuff like that. And then after that, yeah, you do also have to upweight or had a method of upweighting certain tokens in the vocabulary, and in particular, proper nouns was something that needs to be upweighted higher for some reason, because projection didn't seem to capture this. And even then, there are still like worries. So this was where the project got a bit cursed, and our luck kind of run out, I would say.
Indeed.
Yeah, one other like unfortunate hack which like did make the results like a little bit more annoying to place confidence in. When we projected the queries and then like sent that residual stream vector like through the query matrix to like, get our actual query vectors, you have to renormalize them, otherwise the results are like not super good. But the issue with renormalizing is if you've removed everything except the unembedding component, then renormalizing it will boost the unembedding component, so it'll make it seem bigger than it actually was. Like as a very simple example, let's imagine that like 50% of the attention scores were down to the unembedding vectors in the query side, and then 50% of the attention scores were down to like something that was not the unembedding vector that was in the query side. And let's say those things were like perfectly correlated. If you delete the non-unembedding component and then renormalize, you're not changing anything because you've like deleted one component and you've doubled the other component. So you haven't changed the like overall effect size. If you actually wanted to get like a faithful projection, you would have to, delete the component perpendicular to the unembedding, but then keep the unembedding at the same magnitude rather than renormalizing it. I think the results again don't look as good as 61% if you do this.
Makes sense. And yeah, what are the results for the CSPA?
I believe the results just doing QK are significantly better than the results doing QK and OV. In other words, if you go from just doing QK to doing both, it makes it a lot worse. On the other hand, if you go from just doing OV to doing OV and QK, the results don't actually get much worse. Like most of the extent to which this does not like exactly match what the head is doing comes from the OV side rather than QK side.
Do you have concrete numbers?
I think we're talking about the concrete number of just like the whole CSPA, which is in the abstract. I believe it's 79 point something, as far as I remember. Yeah, if you could scroll back to the abstract, Callum, I think we have the key standout number from the CSPA experiment.
Yeah, 79.6. Oh, 76.9.
Oh, oops, I got it wrong. 76.9. But
629 years.
Yeah, I believe it's like upwards of 90%. Like the query, the attention pattern intervention is not very destructive. Almost all the like input tokens that like the attention head cares about are the ones that are highly predicted.
Yeah, no. I guess my biggest concern with CSPA is the experiment showing that at least if you don't clamp the OV to be negative, you allow OV to be positive, that like quite a lot of heads look pretty good under it. Like, I think it's telling us something, but I think that statements like the head looks at the occurrence of a token that is fairly likely to be predicted next is just like not that exciting, or like not that strong a claim.
I think there is like definitely a world in which like maybe 10.7 like really isn't special at all, but there are like a bunch of heads that have the same kind of motif as 10.7, which is like a 10 vector thing that's currently predicted, and they all do like a kind of wide palette of different complicated things, and we just happen to find the one that does the suppress thing. But like there are a bunch of other ones that have like way more complicated OV matrix behavior that we like haven't fully diagnosed or something.
So yeah, I don't know. Zooming out, How well do you think we did? Do we fully understand the head? Why are we getting 76 rather than 100?
Yeah, I think so. Yeah, there is like a small extent to which we could like incorporate a bunch of other like very granular rules about things like semantic similarity and function words. But I think this would have a pretty long tail of, oh, you're adding like loads and loads of other rules, and you're not really going to boost the like explainability of this head by a huge amount. I like think the extent to which we've not explained 100% of this head's behavior is basically the extent to which this head is like not 100% monosemantic. It seems more monosemantic than the average head, and like as we discussed earlier, a lot of that is probably in part due to the fact that it has learned this like very simple and easy to describe OV map. And if you have an OV map which is map source tokens to the corresponding like output vector, at that point you're kind of going to be constrained to apply one very simple algorithm rather than like doing a bunch of different algorithms at once. I think it is like still likely this head is doing a few more things than we like fully understand, and that's probably why we have like come short of 100%.
Yeah, I think I'm like a little bit more positive than this overall. Like the sort of goal was to like describe a basically monosemantic attention head, and we don't get to 100% recovery. But on looking at like the failure cases, which would be either the cases where like projection doesn't work, so we did that sort of like as not as well as could have possibly been done, or the like case where the OV projection has some issues as well and like loses some performance. It doesn't feel like what's going on is something completely different to copy suppression. It just feels like there are just like additional heuristics that are added that also like do suppression in the end, but either the suppression activates in a context where it's not as much that like there's a confident prediction, but some other thing which goes on, or like you attend to token A, but then the suppression actually happens on like a similar token B. I believe there are examples where something like it attends to the word sport, but like suppresses the basketball prediction or something like that, where it's a clearly related concept, but it's not a literal copy suppression. And overall, I think that like it's maybe like a good update that it is hard to understand the language model components. Like they have a lot of extra crap going on in the tail. And 50,000 tokens is a lot of tokens. So it was kind of optimistic to hope we'd be able to have a explanation that covers 50,000 tokens. But I think it's more of a sign of optimism that it's like possible that this thing is like within reach or something. But you will actually run into, if you want completely like end-to-end level explanations, you will run into a long tail of stuff. So I guess that's my overall take about the limitations.
Yeah, like one system model learn. To add to the sport and basketball example, there's one other interesting one where the model is predicting Egypt and it attends to Cairo and it suppresses Egypt. And if you look at the QK and OV circuits, again, you can look at this on that interactive page. This is exactly what you'd expect from looking at the static analysis of the weight matrices. But yeah, it's like one of those things that's in the very long tail of rules that kind of seem like they are in some sense philosophically related to copy suppression, but like are not actually captured by the exact methodology of our ablation that we use here. And yeah, in case we didn't like make this clear, because I think we just like sort of brushed over it, the CSPA is combining OV ablation and QK ablation. In other words, we like both filter for the attention probabilities, and we take the output of things we have not like thrown away at that stage and project them onto the negative of the unembedded. So you can see it like conceptually combines both these two ideas.
Yeah, I think the thing that makes me most optimistic here regarding like did we understand this is, as far as I'm aware, you guys haven't actually found any examples of the head seeming important in a way that's just clearly not copy suppression.
Not a cluster of examples. Like there are always sort of random outliers in any set of like 10,000 elements or something. But if you look at it statistically, like the kind of pattern that you often see, that we often see when we like look at this data is if you like group the examples by how important this head is on them and take an average like within those groups, the groups where this head is most important are consistently the groups where our explanations for its behavior are best. So even though there will like inevitably be some like weird outliers where the head just like happens to push on a token in a way that like affects the loss a huge amount, when you take an average over these data points, you get this like really strong effect that we can like predict the behavior even in situations where this head is like super important.
Awesome. Maybe to close, should we discuss the nuance of whether to use loss or KL as your metric?
Yes, that's an excellent tangent. Thank you. There were a few different things we were batting around when we were considering like exactly how to assess the performance of CSPA as our metric. The basic idea is like if CSPA doesn't change the output at all, then our metric is great. Then like our ablation is great. Our understanding of the head is like perfect. On the other hand, if CSPA completely destroys the head's output, then our understanding of the head's behavior is like basically 0. When we say completely destroyed, we're talking about CSPA like relative to mean ablation. Because mean ablation is the extreme where we are literally throwing away all the information that this head has and like completely destroying its functionality. So if CSPA is like as bad as mean ablation, then we essentially don't understand the model at all. There were a few different metrics that we like tossed around for this, and the two that we like mainly focused on in this paper were the amount of loss that we had explained and the KL divergence between these metrics. So yeah, so we start with loss. When we talk about the like loss explained by our ablation, we can basically say, what is the average amount by which loss changes when you mean ablate this head? What is the average amount by which loss changes when you do CSPA? And if the average amount by which loss changes when you do CSPA is like much, much smaller, then this is great. Our model like explains the effect like pretty well. You can also just restrict to the cases where this head like decreases loss and see whether CSPA like also like doesn't change things very much. You can just restrict to the cases where this head like increases loss and see whether CSPA also doesn't affect things by much. Because if you're trying to explain like the behavior of a head, you don't just want to explain it in situations where the head is like, actively good for the model. You also want to be able to explain it in situations where the head is like actively harmful. The head is doing some algorithm and you want to be able to explain it. This is loss. The other metric that we used for some of these results is KL divergence. In other words, you can compare the KL divergence caused by doing CSPA, in other words, the like KL divergence of the output produced by CSPA relative to the original distribution, compare that to the KL divergence between the mean ablated distribution and the sort of non-ablated distribution at all.
Where we run the model on a given prompt, and we get a probability distribution over output tokens, and that is our base distribution. And then we mean ablate it and get a mean ablated distribution and look at that difference, or we do CSPA and get a distribution and look at that KL divergence.
Yeah.
And a crucial detail is that KL divergence is always positive because it's kind of measuring distance between probability distributions, while loss can be positive or can be negative, because loss is the change in the correct next log prop, which could go up or down.
And yeah, this is the way that we defined the effect explained in this like metric of KL divergence. So yeah, doing a quick sounds check on this. So this DCSPA is the KL divergence between the like copy suppression preserving ablation distribution and the clean distribution. If this thing is 0, then it means that our copy suppression preserving ablation didn't affect the head's output at all. It's like exactly the same as the clean output. And so this whole expression we won. On the other hand, if CSPA is so destructive that we change the distribution as much as mean ablation did, then like this thing would be equal to this thing. And so like this fraction is 1, and so this expression is 0. What we have is like thing that is between 0 and 1, and well, it doesn't always have to be between 0 and 1 when you average over groups. In practice, you find that it's always between 0 and 1. And if it's 0, it means we've explained like basically none of the behavior. If it's 1, it means we've explained basically the whole behavior. This seemed pretty good, but one of the things that we learned during this project is it is really important to figure out whether there is a systematic reason that your metric might be giving you results that look better than they actually are. KL divergence, it turns out, has a kind of flaw related to this, which is very specific to the fact that we were studying the copy suppression algorithm. Essentially, the problem is this. Let's imagine you had a probability distribution P represented in like logits. And let's imagine you like changed one of those logits and measured the KL divergence between this like original distribution and the change distribution. Well, like the change distribution, you just change one of the logits by some fixed amount of X. The situations in which the KL divergence will be largest are the situations in which you change the logit of something that already had very high probability. Because KL divergence is essentially a weighted average according to your original probabilities. So if you're like changing something that already had very high probability, then KL divergence is going to change by a lot.
Yep. Concretely, I believe KL divergence is the sum over all tokens of the probability of that token times the change in log probability of that token. And so if your probability is like a half, then a change of one logit is a massive deal. If your probability is 1e minus 4, then a change of 20 log props, which is insanely large, is just like negligible.
In this thought experiment, now let's imagine that you had like a form of ablation, where the ablation was basically delete this head's effect on low probability tokens. If you did this, it would not change the KL divergence by much. because like deleting the head's effect on low probability tokens doesn't change the KL divergence, because like all those terms have like a really small weighting. But that is kind of what CSPA is, because CSPA by definition like throws away the head's effect on low probability tokens, and it keeps the ways in which this head is like affecting high probability tokens. Because in the QK stage, we're like filtering for situations where a token is already being predicted, and then that token's probability is like then affected. So yeah, this was like the theoretical concern behind using KL divergence as a metric. To recap high-level ideas, KL divergence is essentially takes a weighted average of the changes in logits, and the fact that our metric is one that primarily captures the ways in which this head affects tokens which were already predicted, is guaranteed to look good on most KL divergence measures, or at least that's like what our concern was. It's guaranteed to look good on most KL divergence measures because those are exactly the kind of changes that we would expect not to be ablated. Yeah, also the like precise technical details of this are like not super important. I think the important thing at a high level is like if you're using a particular metric, consider the nature of the thing you're trying to measure and consider whether there are ways in which your metric is like systematically failing to capture some of the nuances in like the thing that you're trying to measure and why it might appear systematically better than it actually is.
Yep. And another more pragmatic lesson is use a bunch of different metrics with different strengths and weaknesses. If they all basically agree, yay. If they don't, boo.
Yeah, so this is a very good point. So you can like theorize, but like maybe there will be some reason in which your metric is flawed and you can't spot it. And like ultimately doing an empirical test is the thing you actually have to do. When we did an empirical test, when we compared like KL divergence to like loss explained, we found the results were like very similar, which essentially removed most of our worry.
See Appendix J for limitations, comparisons, and baselines.
Yes, exactly. There were some other metrics like didn't look quite as good, but we actually felt that, like for instance, I think absolute amount of loss explained didn't look quite as good as a metric. Yeah, overall, there are also reasons why we felt that these kind of metrics didn't really feel as natural anyway, because if you're thinking about absolute amount of loss explained, you're going to catch a lot of noise from the cases in which the head isn't really doing copy suppression, but it's like affecting the output by, a very small random amount that obviously like our metric doesn't pick up on because it's not doing copy suppression. But there are so many situations where the head is affecting the output by some small random amount. And if you're taking the absolute value, these like all add up a lot, and they'll eventually give you like a really large effect. Yeah, if you zoom in on this graph, you can see that in the cases where the head wasn't really important, we're not doing an amazing job like explaining 100% of the behavior, and we shouldn't expect to, because like copy suppression isn't actually going on here. It's only when you get to the situations where the head is like actually more important, like further along in this curve, that it actually is copy suppression. You can see copy suppression happening when you look at these prompts, and our like metric works well to capture this.
Yeah, just to be clear, the dots on this figure 5 as shown are like the percentiles along the like different buckets of how destructive mean ablation is. So what this means in practice is that this dot on the far right is the top 1% of cases where mean ablating this 10.7 head is like maximally destructive. But as you can see on this plot, it does not look as if there are 100 dots there. There's a strong clustering of most of the like cases where you like ablate this head on different token completions, having basically zero effect. And as Callum says, we don't really explain what the head does here very well, but it actually doesn't really matter that much since like the head just isn't doing that much. We would be kind of interpreting noise if we were like doing a fantastic job at explaining those cases.
Yeah, when we were discussing earlier about this head's effect on the output being very heavy-tailed, like pretend that this was a plot of like effect on loss as opposed to KL divergence, because the loss plot looks like very similar to this. You can imagine how just like adding up the x-axis values of these like 5% of points gets like most of the like a good fraction of it.
All right. Any final bids for things we should cover in this section?
I don't really have anything. I guess we can mention the Streamlit page.
Oh yeah, should we just check if the Streamlit page has any glorious graphics we should stare at, admiring your graphic design skills?
So we've seen the anti-induction versus copy suppression
we
thing, which is just the embedded polygraph. It's not very interesting. OV and QK circuits is pretty nice. This is basically a place you can replicate all of our static analysis. You can type in a particular token, in this case, token. This shows you like all of the semantically similar tokens, and also shows you like which words this prediction will most attend to, or which words will be most suppressed when attended to this thing, and so on. Like highlights all of the semantically similar ones in orange. So
Okay, I get cryptocurrency. What does token have to do with pony?
yeah, you got me. Token unicorn pony. It's 3 degrees of separation. No, I would love to believe that's not the case. As one example of a thing that I mentioned earlier, let's type in Berkeley with space in here. Bingo! We have Kelly as one of the top 3, and I think if you go to this, actually, yeah, I think it's if you put Kelly in here, then Berkeley's the top one. Yeah, you can see like the semantically similar tokens are like Burr and Kelly, the tokenized forms, and like these show up really strongly in the OV circuits. And yeah, maybe this is something that like wasn't actually emphasized as much as it should have been, but like crucially, the extent to which semantically similar tokens are like attended to or suppressed by the OV and QK matrices is more than you would expect just by the fact that these embeddings have high cosine similarity. Because like, yeah, the embeddings are pretty similar because the words are pretty similar, but actually when you compare how similar the initial embeddings are to like how much the OV and QK circuits treat them as the same, you actually find that like their differences essentially get like squashed by the OV and QK circuits. It really treats these words as the same much more than their embeddings would suggest. And then, yeah, the pièce de résistance is the browse examples page where you can look at a bunch of different examples from open web text, and you can see situations in which the loss is like more affected by certain tokens. You can also look at things like the logic lens and see which tokens were being predicted at any given point. So like, you know, Anthony Bourdain, you see that Dane is being predicted after Bohr, like the most highest probability one. And there are a bunch of like cute examples of copy suppression that you can spot here. So for instance, in this particular visualization, this shows like how much this head affects the loss at any given token, where blue is like actively helpful and red is actively harmful. You can see that the model is like really helpful at eta. And it turns out the reason that's happening is because the model is predicting ny, like eta ny, just like it appeared earlier here. And what this head 10.7 is doing is attending back to ny and suppressing it. And in this case, that is good because ny was wrong.
Helpful on eta means it's helpful for predicting what comes after eta.
Yes,
not at predicting eta itself. Yeah.
Yeah, it is helpful at predicting that the thing that comes after eta is not ny.
I'm surprised it's not helpful on Bourdain. Like Bourdain comes up 3 times.
So yeah, Bourdain's an interesting one. I think that this also plays into like the point about bigrams and like the times when this head will turn on and the times when it won't turn on. Although I actually think in this case, the reason that this head isn't helpful is because it was already predicting Dane with like pretty much certainty, and so like boosting, even suppressing it a little bit, like actually doesn't change the probability of how much because it's like still basically 100%. The final nice example I want to leave with is the at the peer example. So after the word at, it is predicting peer. Afterward, it is predicting peer. And in both the cases, things predicting is the lowercase version of peer. And it turns out that what's happening here, if you navigate to attention patterns, the word at is attending back to capital peer. The word the is also attending back to capital peer. Remember, a result from semantic similarity, it is the lowercase peer that is being suppressed thanks to that like attention. And it is helpful to suppress peer at this particular position because peer is wrong, but it's unhelpful to suppress peer here because peer is correct. And so if we navigate back to loss, you can see, sure enough, blue because it's helpful, red because it's not helpful.
That is very cute. Also, I am just loving these interactive visuals.
Oh, I know. So fun.
Is this from your fork of circuit space?
No, this is actually just like vanilla HTML and JavaScript. GPT is really helpful.
The attention visualizer is the attention visualizer.
Oh no, sorry. Yeah, sorry. This one is circuit space. It is my fork of circuit space, but yeah, circuit space. Yeah, the other stuff is vanilla.
And this one also, logic lens also seems busy.
Yes, this one is the direct logic attribution of this head. So like, for instance, eta, you can see that the word that is most suppressing is ny, and like also, variants of it. And similarly at the peer, it's suppressing peer, both capital and the lowercase version. But in this case, the only thing that matters is that it's suppressing the lowercase version.
And the link will be in the description.
And Dane, you can see that it is being suppressed, but I guess it just doesn't matter.
And also Bacon, apparently. Obviously, Dane and Bacon are semantically similar tokens.
Bacon Dane.
I should probably cut the model some slack. All right, we should wrap up there.